Hey, we're back again today with a lesson on half-lives. So the rate of radioactive decay. Last week we were taking a look at radioactive decay and we were balancing some equations, and today we're going to look at how fast that's happening. So last week we called them unstable atomic nuclei. Today we're kind of changing that term and we're going to call them radioisotopes, or radioactive isotopes. We combine those two words, make a compound word, radioisotopes. Last week, again, we talked about how they decay to become more stable through a nuclear reaction. And we got some practice balancing them, such as carbon-14 decaying through beta emission to form nitrogen-14. But how fast do these reactions occur? So, for instance, if I gave you 50 grams of carbon-14, how long would it take to decay to nitrogen-14? I know the answer to that is a little bit more complicated than you might expect. The rate of decay is measured in what we call a half-life. A half-life, and we symbol it as T1/2, the amount of time, half of the amount of time, is the time required for 1/2 of the nuclei in a sample to decay to products. The length of a half-life is dependent on the stability of the isotope in question. So here's a list of some common radioisotopes and their half-lives. And they vary. So uranium-238 is fairly stable. And it only decays every 4.5 billion years. So half of it will be gone in 4.5 billion years. That's what a half-life is. Other isotopes, radioisotopes, are a lot less stable. Lithium-5, for example, half of it decays every 3 × 10 to the 22nd seconds. That's incredibly fast. Fractions and fractions of a second. Something a little more mind wraparoundable, polonium-211 has half of its isotopes decay every half of a second. So in 1 second, you lose 1/2 of the first half second, then 1/2 of that, you're down to a quarter of what you started with in 1 second. Carbon-14, what we started with, has a half-life of 5,730 years. So every 5,730 years, half of your carbon-14 sample has decayed. So let's see how we work with that. So here's an example problem. A 50-gram sample of carbon-14 with a half-life of 5,730 years will have how much remaining after 5,730 years? How about after 22,920 years? So these are types of questions we'll ask, and here is how you should set these up to solve them. Go ahead and build a graph, a data table like this. We'll get to graphing tomorrow. So at the number of half-lives 0, time equals 0. This is the start of time. We have 50 grams. So starting right now, we have 50 grams. After one half-life, 5,730 years will have passed. So we add the half-life time. 5,730 years have passed. And to figure out how much of our sample remains, we divide what we had by 2. So half of it decays every 5,730 years. So half of it has decayed, we're down to 25 grams remaining. How about after that second half-life? Once again, we're going to add the length of time. We're going to add the 5,730 years. So 5,730 years plus another 5,730, 11,460. And then once again, we come over here. The 25 we have remaining gets divided in half. And after 11,000 years, we have 12.5 grams remaining from our initial sample. After a third half-life, we get to 17,190 years. Again, we're adding that half-life time again. We'll divide our 12.5 in half, and this time we're down to 6.25 grams. Notice the underline, that's because of these significant digits. We only started with 2, so we should only have 2. I'm not deleting it, I'm not getting rid of it, I don't want round-off error. I keep it, but I underline it to show that it's not significant. Alright, so after the little significant digit aside there, we'll move on to our fourth half-life. We add another 5,730 years. We're now up to the 22,920 years the question was asking for. Again, we take the amount we have, we divide it in half. 3.125 grams is what we'll have remaining. Now we can answer our question. We'll have 25 grams remaining after 5,730 years, and we'll have 3.1 grams remaining after the 22,920. Notice in my final answer here, I've gone ahead and gotten rid of the insignificant digits. I don't want to keep those in my final answer. I only have them here where I might be showing more work. But my final answer, I go ahead and round to the 2 significant digits that I need. Taking a look at another type of example. Strontium-90 has a half-life of 28 years. How much of a 10-gram sample remains after 168 years? So again, at time equals 0, 0 half-lives have passed, we have 10 grams. How about after 1 half-life? Okay, that'll be 28 years. We'll be down to 5 grams. A second half-life will be up to 56 years and down to 2.5 grams. After a third half-life, we had another 28 years. We're up to 84 now, and we're down to 1.25 grams of our initial sample remaining. After a fourth half-life, 112 years now, we're down to 0.625 grams remaining, half of 1.25. After our fifth half-life, it's 140 years, we're now down to 0.325 grams remaining, and after our sixth half-life, hey, now we're at our 168 years. I got there by simply adding the 28 years each time, each step. I finally got there. It took 6 half-lives to get there. And now we have 0.15625 grams remaining. Now we can answer our question. Again, I don't want to put the extra digits into my answer, so I look at what I have not underlined. 0.156 grams of strontium-14 will remain after 168 years. And that's definitely a typo. Should be strontium-90. Taking a look at another example here. The mass of cobalt-60 in a sample decreased from 0.8 grams to 0.2 grams over a period of 10.5 years. So from this information, calculate the half-life of cobalt-60. A little different question here. That's okay. We can use our column to solve it just the same. So at time equals 0, 0 years have passed, 0 half-lives have passed, we started with an initial amount of 0.8. After 1 half-life, we'll be down to 0.4 grams. Now, I haven't added in years yet because I don't know what the half-life is. That's what we're trying to figure out. After a second half-life, I divide that 0.4 by 2, and now I'm down to 0.200 grams. Hey, that's what the question was asking, and I know how long that took. I can go ahead and plug in that amount of time, 10.5 years. So what we're trying to figure out is what is the length of 1 half-life. We know that 2 half-lives took 10.5 years. That's how long it took to get to our sample of 0.2. So what we're going to do here is divide our time, 10.5 years, by our 2 half-lives, and we can find out now that it's going to take 5.75 years per half-life. The radioactive decay of Talcium-206 to Lead-206 has a half-life of 4.20 minutes. If you have a sample that contains 4.88 times 10 to the 19th atoms, and it is 25.2 minutes old, how many atoms were in that original sample at time equals 0? Another way to look at these types of problems. Again, it starts with the data column we've been building. At time equals 0, we don't know what we had to start with. That's what we're trying to find again. After 1 half-life, again, they told me my half-lives were 4.20 minutes, so after 1 half-life, 4.2 minutes. After a second half-life, I'm up to 8.4 minutes. A third half-life, we're up to 12.6 minutes. A fourth half-life, 16.8 minutes. A fifth half-life, we're all the way up to 21 minutes. And finally, a sixth half-life gets us to the 25.2 minutes that they gave us in the question. Alright, so now we've gotten up to the proper amount of time. It took us 6 half-lives to get there. And we know that that sample after those 25.2 minutes had 4.88 times 10 to the 19th atoms. Okay, well, we're going to work backwards this time to figure out how much we started with. So we're going to multiply by 2. So instead of dividing by 2, working backwards, we're multiplying by 2. So at 21 minutes, we had 9.76 times 10 to the 19th atoms. Multiply it by 2. At 16.8 minutes, we had 9.76 times 10 to the 19th atoms. Multiply that by 2. Now we get to times 10 to the 20th atoms at 12.6 minutes. Multiply that by 2, 7.808 times 10 to the 20th atoms. Down to the that first half-life, we had 1.5616 times 10 to the 21st atoms. And finally, our initial amount, we double that value again. We started with 3.12 times 10 to the 21st atoms, talcium-206, in our original sample. So when we were at times equals 0, we worked backwards. We figured out how many half-lives had passed. Again, we multiplied by 2 because we're working backwards. And we got the 3.12 times 10 to the 21st atoms, not grams this time. This time we're working with atoms, in our initial sample. All right, there's your first introduction to half-lives. Take a look at your homework. It's how we get better. Thanks.